this is tutorial 3, model comparison robustness. So we already talked in the previous session about how we can generate hypotheses and then turn these into models that provide more precise predictions. We talked about how we can fit models to the data, and now today we're going to talk about how we can determine which models provide the best description for our data, how we can interpret these models, and that also kind of frames the two parts of this tutorial. So part 1 is model comparison. I want to start with kind of just a very obvious question: what makes a good model, right? And so a very nice quote by George Box is that essentially all models are wrong, but some are useful, right? So never are we going to have a model that's actually the exact perfect description of what we're trying to model, right? But what we want to do essentially is get some useful interpretations from these models. We want to get something we can not just see when we directly look at the data. We want some useful abstractions. And one rule of thumb in terms of how we design our models is that we want them to be as simple as possible, but not simpler. There's this really nice parable by Jorge Luis Borges on the exactitude of science, where he describes the situation where this empire has created a map that's 1-to-1 equally the size of the empire, right? The map has captured all the details of the empire, but it's actually the same size as the empire itself, and that produces a perfectly useless map because it doesn't provide any interpretation, right? And so that's not the goal of modeling. And this is illustrated quite well in this distinction between fitting performance and predicting performance, right? So here's a very classic example. We're trying to model, for instance, the temperature in London as a function of the day of the year. And we might consider different types of model complexity, right? For instance, in this dashed line, we have a degree 3 polynomial. And on this curvy line here, we have a degree 12 polynomial, right? So the higher the degree of the polynomial, the more complex the model. And we can see very clearly that as we increase the degree of the polynomial, we're getting better fits, right? We're able to describe the data much better. But when we're actually trying to make predictions outside of our training data, we see this kind of U-shaped curve, right? Whereas at some level of complexity, the model gets better, but then beyond that point, it gets worse at predicting because it's overfit the data. So typically what we're trying to do in model comparisons is try to figure out this tug of war, right? We're trying to get better fit for the model, but we're also trying to avoid making it overly complicated. We want some simplicity. So this is the tug of war that kind of defines how we want to do model comparison. Now, we're going to talk about some goodness of fit measures. And these kind of map onto different theoretical frameworks, either a maximum likelihood approach, where we're getting a point estimate of the parameters of our model that provide the best fit, or a Bayesian approach, which provides us with distributions. But in practice, we can actually think about these as following kind of two different main approaches. One is we're penalized for parameters. So both AIC and BIC, they have kind of fallen under different camps in terms of theoretical interpretations, but in practice, they're actually very similar and just based on penalizing for parameters. And then a different approach is to directly use prediction error, or for instance, with Bayesian Occam's razor, we're using we're trying to do prediction in a Bayesian way. And this also kind of falls under both the maximum likelihood approach and a Bayesian model selection approach. We're going to talk about some of the preliminaries for doing Bayesian modeling with MCMC, but we're going to go into much more detail tomorrow with Lei's tutorial. So I'm going to start first with maximum likelihood estimation, which is a concept I talked about yesterday, right? And the goal here is to quantify the goodness of fit for a single set of parameters. And I use this theta hat. It's got a nice little hat on it. And because this is what we try to, this is the value of the parameters to provide the best fit for the data, right? Remember, we talked about how we could do this yesterday by getting some argmax over the likelihood, or conversely, minimizing the negative log likelihood, right? Typically in the maximum likelihood approach, overfitting is avoided by penalizing for the number of parameters in our model, okay? Or what we're trying to do is use cross-validations to test the predictive power directly. But both of these, all these approaches use some sort of point estimate of the parameters. Now, in Bayesian model selection, the goal is actually rather how to quantify how a given model captures the data over all the values of the parameters, right? And so this is not only taking the model at its best, which is what the maximum likelihood approach does. It considers all the flexibility of the model under all the sets of parameters. So some parameters might give you very poor estimates, and you penalize for this in Bayesian model selection, right? And so what this means is that we get some natural penalization for models that are too flexible, because under certain sets of those parameters, we're getting very bad predictions. And what this approach does is tries to integrate out over all the possible parameter values, allowing for natural penalization, right? So, but one important caveat is that this is actually intractable in most settings. We can't perform these computations for every single set of parameter values. And this is often approximated either using something like BIC or through MCMC sampling. So I'm going to start first with this kind of approach where we penalize for parameters, and I'm going to talk about both the theoretical interpretation and the actual practice of computing AIC and BIC. So I'm going to start first with AIC, which is Akaka's information criterion. And this is the formula here, and I'm going to break it down. So we already saw this term, right? This is just the negative log likelihood times 2, which is also known as the deviance. And this is capturing how well we can fit the model to the data, right? We perform a maximum likelihood estimate to figure out what the best set of parameters are. And then under that parameter set of parameters, how well does it describe the data? And we calculate the log loss and times 2, okay? So this is very simple. We already talked about this before. And then we just penalize for complexity by taking 2 times number of parameters, right? So here, the number of parameters is used as a proxy for the degree of complexity of the model. It works really well, for instance, with this polynomial example I showed you earlier, where adding kind of a higher degree polynomials requires adding more parameters, adding more complexity to the model. Now, the theory behind AIC is actually quite abstract and very esoteric. It's trying to capture the information that's lost by the model, trying to capture some objective reality, R of X, and we're integrating over all possible data, and the maximum likely estimate represents some kind of degree of distance from reality. Now, this is incredibly esoteric and assumes reality is some sort of constant that's unknown, but we can compute this term over. But in practice, that interpretation is hardly ever considered. But it also has this additional asymptotic equivalence to leave one out cross-validation. So leave one out cross-validation is where you take the data and you iteratively split, leave one data point out from the training data. We fit on the training data and we test on this one left out data point, and we repeat across the whole data set. So AIC in practice is equivalent to this leave one out cross-validation for linear regressions and for mixed effects regressions, and in the limit of infinite data, right? So this is maybe the less esoteric interpretation of what AIC is trying to capture. However, most of the time, people are not only applying AIC to regressions, and they're certainly not applying it in the case of infinite data, right? So rather, what is maybe kind of the more kind of practical interpretation of the AIC is that it's one of the most lax goodness of fit measures we can introduce, and is sometimes more prone to referring an overfit model, although it's maybe justifiable in the use of regression models, and when we have a lot of data that kind of gets us close to this asymptotic interpretation, right? So it's relatively lax. In contrast, Bayesian information criterion has a Bayesian interpretation, although in the equation it's actually very similar to AIC. Again, we have the exact same measure of fit here based on the maximum likelihood estimate. Under the best set of parameters we can find, it's 2 times the negative log likelihood. And then we have a slightly different complexity term here. So here, K is still the number of parameters, but then we penalize by the number of parameters times the log of the number of data points in our data, right? And as you'll see, as long as N is something relatively large, this penalizes the complexity more strongly than AIC does. Okay, now for the theoretical interpretation. In Bayesian model selection, we're typically trying to not look at kind of some objective measure of fits, but rather quantifying the evidence for one model over another. And this is sometimes known as a Bayes factor. So this is probably something you come across before, but maybe the interpretation is a bit confusing or esoteric. But essentially, the Bayes factor is simply this ratio between the evidence for one model over another. When the Bayes factor is 1, there's equal evidence for both models, so we don't really prefer either or. When the Bayes factor is much larger than 1, we're getting more evidence for model 1 over model 2. And then when Bayes factor is less than 1, we're getting more evidence for model 2. So now, So this term here is the probability of the data given in a model. And recall that we have this integral here across all the different parameter values, right? Which is intractable under most settings. And rather, what we're trying to do is that the base factor offers an approximation for the probability of the model, of the data given the model. This approximates the marginal likelihood, this term here, using the maximum likelihood estimate and making some assumptions about the prior. Okay, and BICs then allow you to do this base factor computation based on this formula here. Now, the actual Bayesian interpretation of BIC is not without controversy. And the assumptions that are required for instance, in terms of the forms of the priors are hardly ever met or even unpacked, right? So in practice, most people don't really think of BIC as actually doing a very Bayesian approach to model fitting, but it's actually, in practice, maybe perhaps a more strict approach to penalize it for complexity than AIC does, by using essentially the principles of maximum likelihood estimation. And so these cases where log n is greater than 2, when there's at least 8 data points, it's going to penalize the more complex models more strongly than AIC will. In the code notebooks, we provide kind of a simple set of simulations and model fits. I simulated some data from a Q-learning agent here in a kind of a social bandit task. So the agents are making these choices, where these are corresponding to different arms of the bandit. And here are socially observable choices, though, of course, the Q-learning agent doesn't make use of them, right? So each row is a different agent making their choices. And we're trying to compare two models here, Q-learning versus value shaping, where the true data comes from the Q-learning agent. And we're looking at AIC. We actually get very similar AIC values between Q-learning and value shaping. The value shaping, so Q-learning is slightly preferred. So remember, lower is better for these goodness of fit measures. But when we penalize for model complexity, we see BIC provides more of a clear distinction between these two different models, right? Where we get stronger evidence for Q-learning over value shaping. Now, note that the actual kind of, so each of these points corresponds to one of these agents that we're trying to model. Notice how like between these agents, we have a lot of variability, right? So these values are really interpretable in terms of the relative goodness of fit for each participant or each simulated agent. But you're going to get a lot of variability just due to the nature of the data. Any questions at this point before I continue? This
Yeah, yeah, I just wanted to double check that I understood how these two graphs relate to each other. So each row is a set of choices, and there's 4 of them, each row of points.
Mm-hmm.
And they're each one agent.
Yeah.
And then those are corresponding to the 4 sets of points.
Yeah, exactly.
Okay,
Yeah, right. And when we fit the value shape agent, it assumes that this agent's choices are also informed by the socially observable choices, right? Erroneously, because here it's not generated in that context, but you're trying to see if you can distinguish between these models.
Cool. So the difference between each of the agents is basically what choices they're making. Each of them have different.
Yes, exactly. So each of these points corresponds to one agent, one target agent being modeled. Okay. Right. Okay. Sure. Thank you. Right. So if I'm doing a regression, like linear regression, or mixed effects regression, then it seems somewhat justifiable to use AIC because it actually has this nice interpretation that it's essentially doing this like leave one else cross validation. But most other cases where we're doing these kind of models that are very much not in the linear regression format, BIC I think is preferable because it's less likely to make this overfitting error, right? You're going to be more conservative in choosing a simpler model.
Linearized linear model. How does linear model?
Yes. Okay, so I'm going to move on now. So these are the kind of simplest approaches to doing model comparison based on penalizing for parameters. They're a great beginner approach, but for more robustness, using things like cross-validation loss, so cross-validating the data and doing MCMC under a Bayesian framework provides much more robust estimates, and it's much more the state of the art. So I'm going to start with cross-validation. which I mentioned briefly, but we're going to develop some better intuitions. So then rather than penalizing for complexity post hoc based on this kind of assumption that number of parameters is a good measure for complexity, we can actively test the predictive accuracy of a model through cross-validation. So what we're doing is we're iteratively splitting the data into training and test sets, right? And then we're fitting the model on the training data, and then we're testing on the test set. And we're doing this iteratively through all the different test sets. So yeah, we can estimate a maximum likelihood on the training set and then predict on at a sample on the test set. And then what we're doing is we're measuring the good of fit as the sum log loss or the log likelihood, negative log likelihood for all of these out of sample predictions, right? We're summing up all these blue squares that we're testing on. So this is kind of the loop that we're doing. We're breaking up data into different slices, estimating a maximum likelihood on the orange. This might be some for a reinforcement learning model. We're getting some best set of parameters from the orange training data, and they're making a prediction on some unseen test data. And then we're summing up overall this test data to get our cross-validation log loss. There's multiple approaches to doing cross-validation. We can, for instance, if you have a natural distinction in your experiment based on different rounds or blocks, we can leave one round out for our cross-validation. This is important to make sure that you don't have maybe any learning effects over rounds that might give you biased estimates of your parameters. You want kind of consistent behavior across different rounds to avoid any kind of temporal dynamics that you're in your modeling. You can also do k-fold cross-validation, where you kind of break up the data into arbitrary slices in k equally sized slices if there's no natural structure in the data that you have. Or you can even do the most extreme case where we're leaving at a single data point and iterating over this. So some of the advantages of different approaches is that, for instance, this leave one out cross-validation could be very costly if you have a lot of data points, right? So essentially, we're doing maximum likelihood estimation n times based on how many data points that you have. So that might just not be feasible because we're essentially making the whole model fitting procedure take that much longer. There's a question here. Let me pass the microphone.
Why do we not leave out a proportion of the data set rather than a single data point or a round?
Yeah.
Like, but if there's no like structured round,
then we create arbitrary slices.
Proportion of.
Yeah. So if there's no natural structure in the data, right, you can break it into k equally sized slices, right? Or sometimes also called folds, right? So this is k-fold cross-validation.
Okay. From the drawing, I thought you were leaving one out every time down there. Okay.
Yeah. So we're leaving one fold out or one slice out, right? However you want to slice it, right? So it's somewhat arbitrary and it's based on your data, right? But I guess like the more you leave out, maybe the more robust your predictions will be. Yeah. But maybe also more variability because depending on how much data you have to estimate your maximum likelihood. Okay. So now we're going to get a little bit distributional to talk about Bayesian model estimation. And this is kind of meant to be kind of a preamble to what Lei's going to talk about in more detail on Friday. And I wanted to just first point out what is the benefit of Bayesian model estimation. It's certainly much more complicated. It's more technical, but why are we even getting distributional? Well, the main point is that we're not only getting this kind of single point estimate of where the best sets of parameters are, right? And as we showed you yesterday, sometimes that maximum likely estimate is not stable or always very accurate, right? But rather, we're going to look over the entire distribution of parameters. So here's some plots from one of my past papers where I'm modeling kind of the value directedness and exploration parameters for participants when they're put under time pressure. We can kind of see that we have these different distributions of what those parameter values look like. And rather than only assuming participants are independent samples, like each participant gets its own maximum likely estimate, we can describe them, we can model them with having some hierarchical relationships, that all the population has some similarities. Each person is a sample from that population. And this allows us to kind of get what's called shrinkage a terrible term, but essentially it means that we kind of get more accurate population level estimates, because ultimately when we're getting participants sampled from the population, we're trying to describe some sort of general cognitive aspect about them as being representative rather than each participant separately. And so this allows us to get better population level estimates and avoid things like outliers influencing our data too much. And I've already talked a little bit about Bayesian's Occam razor, which is that we can naturally avoid overfitting because we're evaluating the model across the entire range of parameters, right? We don't only evaluate the model at its best, but also at its worst and across all the different ranges of the parameters. So first of all, what is distribution over parameters, right? So specifically what we're trying to get at is something called a posterior distribution over parameters. So previously we only used the maximum likely estimate to get a point estimate, where the best parameters are this kind of theta hat. But what we want to do in Bayesian frameworks is to model the full distribution of parameters suggested by the data and our choice of models. And this is using Bayes' rule. So what we're trying to define is the posterior probability of parameters given the data and the model. And this is proportional to some prior over the parameters in the model. And then it's multiplied by the likelihood. Under those parameters in the model, how likely are the data? So this is the posterior, which we want to compute using Bayes' rule. This is the likelihood, and this is the prior. We also have a denominator term, which is called the model evidence, which is intractable. And I think later we'll talk about that more in detail. But here we're going to focus on these components. Now, with this intractable equation, what we want to try to do is approximate this in some sort of computationally tractable way. And this is often done using Markov chain Monte Carlo. So the problem is that we have a probability distribution that is difficult to compute. And so what we do is we acquire random samples that approximate this distribution. So there's two main components in Markov chain Monte Carlo. There's a Markov chain. This is simply a sequential process where each random sample is used as a stepping stone to generate the next sample, right? So this is this very simple concept. We generate a sample, we use that sample to then consider the next one. We only have to consider that previous sample to generate the new one. We don't have to consider the whole previous sequence. And it has this nice special property that this Markov chain has as some equilibrium distribution, this target distribution we're trying to apply. We're trying to approximate, and I'll show some intuitions for this on the next slide, right? So this is why we use the Markov chain. And then Monte Carlo simply refers to this famous casino, where there's this idea that the law of large numbers, when we acquire enough randomly drawn samples, we're going to get an approximation of the underlying distribution. Well, I flip a coin enough times, I can use the number of heads and tails to approximate the probability of heads and tails. So we have some pseudocode available in the code notebook. Lei also has a very nice package for doing MCMC, but here I'm going to describe one of the simplest forms, which is using the Metropolis Hastings algorithm. So we first sample some initial points, and then for each other time point, we're going to define some transition distribution. So this is the Markov chain property that based on this point, we're going to have some distribution that defines how we consider our next point. From our next points, we're going to compute the likelihood of the data given these parameters. Recall yesterday we had this likelihood function. It's very easy to evaluate, right? Given a single set of parameters, it's very easy to evaluate how likely the data is. And then given that likelihood, we're going to accept that sample with some probability proportional to how much of an improvement it was over the previous points, right? So here's an example of where we've gone over here and the likelihood is actually lower, and we've decided to reject that sample. But these filled dots are all successful samples that we've accepted. So each point, you're generating some proposal, we're calculating the likelihood, and we're accepting it based on the ratio between this new likelihood and the previous likelihood. We keep repeating, accept, 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 reject, resample, accept. And what happens here is, like, based on this histogram, we're describing the posterior distribution that we're trying to model. Yes. Want to pass the mic?
I just wondering, does it matter in which order we iterate the parameter space? Like, if we have we have multiple parameters in our model, does it matter for this procedure?
We do it jointly.
Yeah. So
yeah, at the same time. It's done jointly at the same time because the likelihood is defined by all the parameters in the model. You can't evaluate it for a single parameter, a single one of the parameters of the full set.
No, sure, but like when you like change the parameter, like
We change all the parameters simultaneously. Yeah, we have to define some distributions, some transition distribution over them. And some more technical questions I think we'll cover more in Lei's tutorial. And here's this example of how this works, right? We're doing these accept and reject steps. And then here, this density is modeling the posterior that we're trying to get. So pretty cool. We can do this iteratively, right? Each single time we're doing one likelihood evaluation, which is quite cheap. And in the end, we get this distribution. Now, there's a number of different MCMC samplers. Stan is a very common one, which has its own kind of programming language, but it can be accessed via R, I think maybe also Python, but Python more commonly uses this PyMC approach. And we can and the main kind of decisions we have to make are what distributions. We're going to model different aspects of our model, like what is a prior distribution, right? And essentially the language of distributions is how we define these models and how they relate to one another. So this is a form of plate notation that's commonly used to graphically depict these Bayesian models. And so this is just meant to be a bit of a kind of an overview of this. And in the code notebook, I also provide some Stan code where we estimate the posterior probability of the alpha and beta parameters for Q-learning agents that I've simulated in here. Are the results where the dashed line are the true parameters, this vertical dashed line, and this histogram represents what the posterior looks like, right? So we're getting reasonably good estimates, but there's still some noise because we haven't generated that much data. There's still some uncertainty about what the parameter values are. And I promised, of course, this is a model comparison tutorial. And in Lei's tutorial 4, he's going to talk about how we do model comparison with Bayesian approaches. We're using something called this widely applicable information criterion, and it's somewhat analogous to AIC and BIC, which I've introduced previously. But the main difference is that we're not only estimating this goodness of fit based on a single point estimate, but we're doing it over the entire posterior distribution. And we're doing it in a way that kind of does a bit of this cross-validation type prediction accuracy. So it kind of combines both of these different approaches, okay, but uses the full posterior distribution of the other parameters. So that's the summary of the model comparison framework. Of course, there's some others, but these are kind of like a nice introduction to how some of the most common and some of the most common approaches are in model comparison. We looked at approaches that directly penalize for the number of parameters using a maximum likelihood estimate based on AIC and BIC, where BIC has a somewhat dubious Bayesian interpretation. And we've looked at prediction error via cross-validation loss, which uses an iterative set of maximum likelihood estimates, but then directly predicts them out of sample data to get better, kind of a better estimate of how well our model predicts. And then MCMC uses Bayesian Okay, so is the screen shared properly, Alex? Okay, so I can try to annotate this and draw this, right? So one common approach is to define R squared, which is based on 1 minus, I guess we can use something like BIC or AIC. I'll use NLL for now of model 1 over model 2. I think I had this in the right form, right? So when or maybe this is a null model. I'll call this model 0, right? So when our model 1 has much less log loss than this term is small, and then this is close to 1. So we get R squared close to 1. When our model is equivalent to a null model, this term is 1, and we get R squared is 0, right? So this is a way to evaluate how much of the variance we've been able to explain with our model compared to a null model. And permutation tests are one way to get a random baseline. But for kind of these kind of reinforcement learning models, you can just assume a policy that's equally likely for all the choices that you have. And that's actually done very simple to do analytically, right? Hope that helps. So for the folks on Zoom who missed a little bit of the session, what we're doing right now is that there's no one on Zoom, okay. For the, yeah.
Maximum likelihood.
Yeah.
Can't you use the MCMC also for maximum likelihood?
Yes, but that's kind of defeats the purpose, right? I mean, in the end, you get a distribution of your posterior. You can maybe take the mean of that posterior, and that's something that's so actually what sometimes people do is take the posterior mode is maybe a more accurate central tendency way to describe the Bayesian results. But the maximum likelihood is based on a single point estimate. So there's no point, right, of doing.
But how is it then? Like if the likelihood is complicated, how do you find the minimum or the maximum?
So when the likelihood is complicated, right? So it's hard to find the maximum likelihood, right? So remember I showed you this one figure in my tutorial yesterday where you have this very like rugged likelihood function, right? There it's really difficult to find, is you can never guarantee that you found a global optima. And so this is why the Bayesian approach is maybe better, because we're getting a good picture of what the overall likelihood is like, right? And so then we're getting much more diverse samples. And in the end, those are all contributing differently to how we get this posterior estimate. No, I don't think you do that. Oh, okay. I think it should be base art, but maybe.
It's not,
It's read.csv. Oh, okay. Sorry about that. I think that was a typo. I'll fix that in the code notebook. Yeah, yeah. Yeah, sorry about that. So if maybe we're trying to run this, it should be read.csv. There's a typo there. Oh, and so that other one is a bit different package, right? Okay. Yeah, okay. So it is correct, but you have a needed package for it. Yeah.
My rebel ran over his-
It's like steaming.
Okay.
It's a very small data set session. Yeah. Yeah, so just to reiterate, the main goal is to then fit this for all the different simulated participants across all the rounds. Here I've only shown you, I think, for a single round, and then describe their overall goodness of fit using something like AIC, BIC, or cross-validation. I don't expect her to start and say. Although if you would like to, I would. Given the being of the content. Doesn't have more ability to do it. This is like a meter. Is it like radius? That shouldn't be. It's right. So how many? Yeah, so there's two different. So whose name is here?
He was saying he was happy to actually go with us. Yeah, yes, so I went to where I have, but it's also.
It should be.
Okay, I think it's a begin with. I'm pretty sure like
This is it's 25, so it's a component on the episode operation.
was these ones are these money for one each of the. This is right now, this is it.
For those who don't have actually a local hub environment now, I've just shared the link to the answer to the cloud. I've shared in a Slack or it's great to go to the cloud environment.
Yeah, sorry. I don't have this.
Yeah, I'm just trying to, my inverter. But I don't know if it's my chart.
Maybe it just fit all the way into the.
Well, I've had these two work together, but maybe
Maybe it's not fitting
fit
it.
all the way,
Yeah, exactly.
yeah. But it was working yesterday, so I don't know why. Yeah, because of this. Mine also. I mean, no, I didn't like destroy it. I'm like, yeah, I'm just.
There's a few that like part of our international block and
Yeah, my feelings, that would never look like that, but I would try doing it on the again.
I would also say that you guys probably don't expect it.
I mean, if people have made us, it's, they don't have to do anything with like, something that you'd be like, we can go to this, right? We go quickly.
Yeah. Yeah, in this role, could have.
It's fine.
Great.
Anything that they don't do like huge roots at all, that's, you know, like, oh, actually, you can't hold your piece of art. Silly.
Yes. So it is agents who in commit the same agents as the media.
No, because each data set has a different signature. So all the agents in Comet are one type, all the agents either are different type.
And they're different.
Each be splitting each of them separately. And each agent has their own parameters. Right, so it's parameters, not parameters.
And comet and meteor are different paths.
So they're the same task, but it's different population.
Okay.
It's console.log. But it's actually not doing that, it's
Right,
just.
it's all on the, so I don't know, I decided to write the
Yeah, so basically it's creating. And then that
yeah.
upper. So this is the maybe one of the thing that. And it's. And then this is the or
So like,
so basically the first, so the first one
either gonna like copy that
like
based on the next choice, like the base and all the value.
and then it does that for multiple exoplanets. So this is a model of the one, and then that model, we'll see how well that model fits this one by looking at the values that are and then you use that for a different.
Yes.
And then
But then we only use our
and so all of these outputs, they're not labeled, so it's kind of confusing, but it was basically just showed the order.
basically for the dollar sign, it's like then do that.
That's right, yeah. So my guess is, I don't know if you need to look at the documentation for this, but whatever it is, it's creating some object that has these products inside. And that's, yeah, it's like, this case. That.
And you can see everything as long as
Yeah. I know ours. They also use like arrow signs.
I guess you have two. Right. So where does this value come from? So this is more single data, but near data.
So it's quite a connection to it.
Yeah, I just caught it.
There's
But that right? Yeah, that's like such a huge, like to zero with like match.
So yeah, one thing that you should do
Okay,
is instead
so
of.
that's
to like label it.
that'll be relative to what.
Do like
Yes.
constant dot
Right, so actually one very simple way to do this, like with
this one.
this and choices, right? So the blah blah. 1 over 10.
Oh.
It's a plus or comma. And then time the number of choices. That's the data set actually is 25 rounds. 25. Okay. And then it's like round. That's ours. You're like everything is around.
So it's kind of like Jupyter Notebook where like
That's not-
you run each time. But you can also run just like
Actually,
that.
that's so it's actually better than chance.
Oh wait, this is.
Yeah. If you have any questions, put your hand up. I can buy. Are you cutting up your task?
Yeah. Okay. Okay, yeah.
And you actually see, like, I do it here already.
Yeah.
Right, and I usually apply it, right?
This is how it works, like when we like fit in packages. All the what packages would you use? For example, BRMS.
The RMS is a regression vector.
Yeah, but they also have
Okay, I've only used it for regression. I mean, it has categorical length functions, and then you would, but you're not, it's kind of a different framework. This is kind of more of a reinforcement learning. Framework, right? So I wouldn't necessarily, and also VRMS is Bayesian, right?
Yeah.
Understand that. So I think that's a different approach. You're like, that's a regression, you're describing behavior, but here we're describing it as a generative process. Right, I mean, the regression kind of is also kind of a generative process, but it's maybe not trying to be such a cognitive description, right? Here we're generating choices, right? And we're finding like based on that.
But I mean, what if we do this computer for agents of the law?
You can also do it for individual rounds, right? But it's actually not meaningful because then when you do it all for each agent in multiple DICs rounds, right? Rather than estimating, like if you do one maximum like the estimate of the whole data set across multiple rounds, right? You're getting one estimate. So if you do cross validation, what you'll do is you'll maybe predict on the out of sample round, and you sum that up, and you get one. You can use negative log confidence cross validation models.
Right.
So that's often what I try what I do. And then your estimate of parameters, well, that's based on each of those cross validated mathematical estimates, and usually I aggregate them based on the median or the mean as a way to get that solution. Yeah.
You could technically generate right, so that you support all the all the generate those for all things.
There's 25 rounds that were. Six rounds. Yeah, I guess we should make this call. Yeah, and then if this is the, I mean, very, we can see, saying that the next thing. Or like you know, so this is for each, like, system looking better. Yeah. Okay.
Oh, it's already.
I guess the idea should more than like this. Yeah, so for each, yes. Almost that much.
Sorry, yes. This will also let me put my.
Yeah. Some of all the commercial.
Yeah.
All I did was just. But it means the version of one. Okay. Able to that's one. I have a bunch of many things.
Yeah, you could do things other than stuff. You could do like something that.
Why just do that? Yeah.
Oh, yeah, that's literally, I was like, okay, we're doing all of it, and I'll do something on each one. But
I know this. Yeah.
that's only a good, but they're already doing. Basically, my plan is to install this something just for all the. But
So we're going to wrap up in a few minutes. People still need a few more minutes to finish this off. It's also okay if you don't complete this, but this is a chance to kind of get your hands on experience with the data, right? And so maybe take some transferring from theory to practice. There's kind of some other challenges maybe you've addressed now that maybe will make things a bit easier in the project work. Should we give you a few more minutes, or does anyone have any like intuitions behind which models were in the different data sets? Should we give a few more minutes then? How about 5 more minutes and then we'll continue, okay?
So, so the target region is same. And there's some of the
Yeah.
agents. We're basically trying to characterize what is the decision bias, the social view, or the value shaping. So it takes in, so basically it's basically just filtering the data so that you're only fitting your model to one of the agents instead of both.
So like you get the data, take the data, and you can
Yeah, exactly. Yeah, so basically that allows you to run the and give that value just for a specific user.
it works.
You can generate a plot from if you calculate the MLEs like each agent, then you can plot the value for each agent. So then you can see how accurate the model was, and then you probably don't need to but maybe you could.
That sounds awkward. Yeah, but that's exactly right. Okay. You want to estimate the model separately for each agent, because each agent has different parameters. Right. Each participant will have different parameters.
Yeah. Yeah. I think you can use either. I don't know if it's what this is. But I mean, they both work. So I'm guessing they're just different syntaxes.
Yeah, I'll come back. Sorry.
I use this again. As you can see, not in the hard line. Yeah, I use it for data.
Oh yeah, these same data. So I just use it for this. Yeah, so it's 10 options. It's a picture of the I was also
Yeah. It's about option. Person in Tom's squad, which is basically yes, which is good. And I finally learned how to use it. Yeah, really good. Yeah, we can usually the set and then one is going to look at the subset. It's really good. If I can which has the point of them, but I think that's what it is. But it's having something. Or like the oh yeah, so it says
All right, thanks everybody. I know you probably can work on it for much longer, but this is just meant to be kind of a chance to look at the data and try to run some of these functions. At this point, does anyone have like a guess at which models were the best description for each of these data sets? So for Meteor, for instance, who thinks asocial learning? Who thinks decision biasing? Value shaping? Okay, so he has a couple of hands, right? So that's correct. And for the Comet data set, does anyone have any estimates? You just decision biasing, great. So that these were actually the models we use to simulate the data, right? So here we're actually able to distinguish between these two different social learning strategies, right? Where decision biasing uses social information, fit level of the policy, and value shaping integrates it at the level of value representations, right? So this may seem very subtle, but here we can very clearly distinguish these two different patterns from data through model fitting. So this is a good example of why we do this. Okay, so we finished this exercise now, and I'm moving on to part 2, which is robustness. And the goal here is to talk about some robustness checks to make sure that what we get from these model estimates are meaningful, right? So beyond just having models win, we also want to make sure that models are recoverable. So model recovery is an important method that allows us to distinguish between whether the data can actually distinguish between the models we're considering. What you just did now is a good test for this, right? I've simulated data from these two different models, and the fact that you can reliably recover the true generating model back tells us that both the models we're considering, the task, and the amount of data we collected allow us to do so. This is not always the case, and so this is why it's helpful to perform model recovery. Now, beyond just only getting the right models back, we also want to make sure that the parameters we get back are also uniquely capturing what we use to simulate the data, right? And so parameter recovery provides a method to look at can we reliably recover the same parameters. And lastly, what we also want to do with models is that we can simulate data that resembles the data we collect from participants or that we observe from animals in the wild, because they're not participants. And what we want to do with this simulated data is to make sure that we can recover the same patterns of behavior that we've also observed, right? Some models, they can predict quite well, but they can't learn, they don't learn the same way. They don't make the same pattern of choices. They don't make the same exploration patterns or other types of specific behavior patterns, right? And ideally, our models should also be able to simulate these as well. So we're going to talk first about model recovery. And the basic idea here is that we're going to take our model, simulate some data, and then we're trying to estimate the set of models we're considering, the set of hypotheses we want to test, and try to see which model provides the best fit. The parameters that we put into the simulations can either come from some a priori best guess. It's often best to run this before running an actual experiment, because the worst case scenario is that you run this afterwards and you realize actually your experiment's not well designed. It's not doesn't allow you to distinguish between your models. Therefore, you've wasted a bunch of money and you wasted a lot of time. But it's also helpful to do this after you've gotten participant data as well, because you can put the estimates that you got from participants and see if you can recover those models back. So what we do is we take these parameters, either from some a priori guess or our parameters. We parameterize our models and run some simulations, and we get some data. And this data should look identical to the type of data we collect from an experiment. Then what we do is we use our model estimation procedure on the simulated data, and we estimate different fits. And we're trying to see how often does a correct model provide the best fit. So not only does this maybe tell you something about whether or not the experiment design or the models you're considering allow you to distinguish, but also your model estimation procedure, right? So this could also be a way to kind of stress test whether your model estimation procedure is reliable enough in order to identify the best model. Model recovery is often described using two different matrices. The first is a confusion matrix, and the second is an inversion matrix. And I'll go through what each of these mean. So the confusion matrix tells us that given a simulating model, so we know what models simulate which data, what's the probability that a different model provides the best fit, right? So here's the simulated models on the rows, and the best fit models on the y-axis. Sorry, on columns here. And these numbers here represent the probability that for a given simulated model, that this model provides the best fit for the data, okay? So what we want to see is these nice clean diagonals, but we also get some cases here, for instance, when model 3 simulated data, actually 1/3 of the time, model 1 provided the best fit, right? And we see these patterns here. So what this matrix tells us that which alternative models mimic a given simulation model, right? So here what we're seeing is that model 3 and model 4 can be quite easily mimicked by model 1. Okay. Now, perhaps more informative is the inversion matrix, where we essentially use Bayes' rule to invert this from likelihood to posterior, where we often assume that the prior is simply just equal probability for the different models. There's some more information in this Wilson and Collins eLife paper, which is a very nice resource. What this inversion matrix tells us is actually maybe more informative, because when we fit models of participant data, we only ever see which model provided the best fit. We don't know what the true generating model was, right? And so what this tells us that if a given model wins a model competition, how likely is it to be the true generative model, right? So for instance, here we see kind of a different pattern, but what this tells us is that, okay, so if model 1 is the best fit model, what's the probability model 1 also was a true simulating model? And here we see, right, that maybe it's only 50% likely that it was actually the best, the true simulating model. There's also some probabilities that it also belonged to one of these other models instead, right? And so this is quite different from this matrix here, because of course model 1 always fits model 1 best, but it also has this problem because that it mimics model 3 and model 4, such that when model 1 wins, it's not actually that strong of a signal that all your participants are actually just model 1, right? You don't know, you can't tell if they're truly model 1 or their model 1 is mimicking model 3 or model 4 like behavior. Any questions?
Does that mean that model 1 is more general?
It could be perhaps too flexible, right? And what this means is that it's perhaps too flexible, and your model comparison procedures maybe not penalizing enough for that extra flexibility, perhaps. Maybe you don't have enough data, right? And so these are all kind of ways to potentially solve this issue, and identifying this as early as possible is usually the best way. Question here.
Yeah, and what accounts for the variance of like the choices based on like the simulated model through this like a stochastic?
Yes, exactly. So like we talked about how these policies describe a probability distribution over choices, right? So it's always stochastic, right? So, and you want to have the stochasticity, right? Because behavior is also not deterministic. So you're always going to have stochasticity, and it's not a given that all models can recover themselves. But ideally with enough data and with a well-designed experiment, you can tell them apart. And so these are providing diagnoses for how you can do this.
But if that's true, wouldn't it be like really unlikely for, like if there was a true process happening and then the model captured it, then surely it would be not capture exactly because of capacity, but like surely it would be very unlikely that different model that doesn't represent a true process would better capture it on the times where it doesn't capture it.
It's unlikely, but for instance, if you're using maybe like a very weak penalization of complexity, a more complex model that has additional mechanisms that are essentially not contributing anything could still provide a better description. And remember when I showed you this kind of temperature of London graph, is it actually described by this degree of 12 polynomial? Well, maybe it provides a better fit, but it's not actually predicting better, right? So if you don't have enough penalization of more complex models in your model comparison, then this can also happen. Yeah. Okay. So beyond just trying to see if we can recover the true generating model, we also want to recover the parameters as well, reliable parameter estimates, right? So the goal in parameter recovery is to determine if the parameters are distinct and behaviorally specific. From the behavior, can we recover what the true parameters are, right? So here we're often either using participant parameter estimates or some prior guess to simulate data. So we're simulating along this x-axis, different values of parameters. And here we're using alpha and beta, again, from this Q-learning model. And then the y-axis represents the parameter fits, where most of them are in red, and then these gray dots are outliers from the data, right? So in general, we're able to get pretty good estimates between these two parameters, but we're also getting some outliers here as well. And what we typically measure quality of fits based on some sort of correlation, right? Maybe your parameters are not linear, they're maybe in log space. So sometimes using a rank correlation like Kendall's tau is also preferable, right? Because we don't necessarily care about the exact value of the parameters, but that they're just kind of have the relative rank values in the data. And so the process is very similar to model recovery. We run model fitting to estimate parameters on the simulated data across all these different values, and we're trying to see if the parameters correspond to the simulated parameters as well. Some kind of additional ways you can augment this is to, for instance, do some counterfactual parameter recovery by systematically modulating parameters that you got from the data. So for instance, keeping one of these parameters fixed and then modulating the rest of them across some plausible range. So you didn't get data in those configurations of parameters, but you might have in this parameter recovery test if you can also reliably recover parameters across a range of plausible parameter values. I ran some simulations in the code notebook based on a very small amount of simulated data, right? So in general, these look quite good. So this is based on this Q-learning agent. Here's what the true alphas were, and here are the estimated alphas, and same for beta. But we get one outlier here for beta, right? So we actually see, but in general, so that kind of influences the R correlation quite a lot, but in general, they're quite reliable. Beta is kind of on a log scale, so you might not want to use a linear correlation. And certainly you want more data than what I simulated here in order to get more reliable estimates, right? But in general, this is just a quick test of this robustness check. Now, the third robustness check I want to mention is that we don't only want to use model fits as a way to see which model is the best description of behavior. We also want to see if our models can reproduce important patterns in our human data as well. And this is really nice text paper by Stefano Palminteri and colleagues. And Stefano was one of our instructors last year at COSMOS. And here's just a very simple example where looking at kind of a different choice variability across sequence length, humans have this are sensitive to this sensitive to sequence lengths in their choice variability, whereas this one model here is completely insensitive, right? And so what you can do is falsify certain models that don't capture behavioral patterns, whereas this winning model here is also able to capture the sensitivity. In some of my own experiments, we've looked at kind of predictions of unobserved value estimates. It's quite noisy, but we have one null model that makes essentially no distinction, and one model that captures some correlation here as well. Right. So what we want is models that can also capture human behavior, not only predictive choice as well. And here's another example from a recent paper that's in press right now in Nature Human Behavior, where we're able to replicate different learning curves across ages. Right. So humans here are in these gray lines of the error bars, and we look at children from the ages of 5 and 6 up until adults to the age of 55. And our full model is in black, is able to capture both of these decaying learning curves and also provides the best fit for the description of the data. So I just want to conclude with what I call a general recipe for cognitive modeling. This is not a fixed set of step-by-step instructions, but rather it's going to require it's an adaptive set of principles. And maybe some of you know this show Iron Chef. I really liked this when I was it's one of my guilty pleasures, but in Iron Chef, you're always presented with a different secret ingredients, and it's testing how well you can adapt your skills as a chef to these different challenges, right? And this is exactly what I want you to do and to take away from Cosmos. We're giving you some set of adaptive principles, but ultimately when you're applying it to your own research, you're going to have some sort of different secret ingredients, right? And you're going to have to rise to the challenge and adapt what we teach here to your specific situation. So this is kind of what the general recipe looks like. First of all, what are your hypotheses? Always start with hypothesis-driven research. There's too many possible models you can consider, and so you can't just do this blindly. Start with hypotheses, start with theory. But beyond just having verbal theories, the advantages of models is we can make them precise. We can describe the specific mechanisms that we think correspond to our hypotheses, turn them into models. Then what you will need to do is estimate the model parameters and perform model comparison, and you need to figure out how you plan to do so. Are you going to use maximum likelihood estimates? Are you going to use Bayesian modeling? Are you going to compare based on BIC or AIC or cross-validation, right? And so these are the decisions you need to make. We've shown you a range of different kind of approaches, from the very simple and basic, the more complex but more robust. And tomorrow's tutorial on MCMC sampling will be much more in depth. But it's not always most complex approach is the best, right? That's not always the case. You have to choose kind of what's the appropriate level of complexity for your research question, and also your own abilities as well. Ultimately, you're going to figure out, you're going to have to choose a method that you can justify and that also matches your research question. And this is kind of related to point 3, is that you want to check if your modeling framework is robust, right? And you can test this by doing things like model recovery or parameter recovery or simulating data before you run an experiment. And this might also allow you to kind of figure out which method of model estimation, model comparison is right for you. If your robustness checks fail, maybe you need to add more sophistication and more robustness to how you compare your models. This is often kind of the right point to then collect data, right? I know most people sometimes do this much earlier, but I think that once with a modeling framework, all the work is done, right? You just had to hit play essentially when you put your participant data in, right? And so this allows you to make sure that your framework is appropriate for the research question and that your models correspond to interesting but distinct hypotheses. And then step 5 is very simple, actually. Analyze and interpret your results. You've already done a lot of the work. Just hit play and maybe make some more tweaks and maybe rerun some of these robustness checks based on the range of parameters that you actually get from your participants. And this is step 6. Test if your recoverability still works with the actual participant parameter ranges that you get. And like I said previously, ultimately, this is just a general recipe. Ultimately, what you're going to have to do is whichever you can justify to reviewers, right? And this is ultimately the kind of the main guiding principle. Like you're going to have to, you're going to be treading uncharted waters in the research that you do. And you're going to ultimately have to make tough decisions about what is the most justifiable way to solve these new novel problems that you face as a scientist, right? And you're going to have to figure out how to justify both to yourself and to reviewers. I'm going to finish with some social learning specific challenges. We tried to present a very general framework here for both animal and human behavior and both asocial and social learning. But I'm focusing on some of the more specific social challenges here. We talked a bit about this yesterday, but social learning specifically has frequency-dependent fitness, meaning that both the performance of real and simulated agents don't depend only on their model parameters, but also about the makeup of the group they're interacting with, right? And so yesterday I showed you some evolutionary simulations as a method for figuring out what is the normatively best solution. But when we're simulating models, right, we're not trying to get at a normative description. We're trying to get at a descriptive model of what people are actually doing, right? So this poses some potential challenges in simulating behavior. We also talked about, we mostly focused on very simple social learning strategies, such based on conformity bias, where we essentially treat all individuals as the same, right? We're just only looking at the frequency of choices that are made by the group. But in practice, much of social learning is selective, right? Based on successful or prestigious individuals. And it's also maybe adaptive. We're copying when we're uncertain, but maybe we're relying more on individual information when we're confident. And so we need more models to account for these types of biases and these types of more sophisticated social learning strategies as well. Julian Hauer-Ettinger will give a talk tomorrow morning on using theory of mind, and we can also consider much more complex forms of social learning as well. But here we've just focused on providing the foundations. And yeah, so we only briefly touched on theory of mind. Modeling it is incredibly difficult, even using very simple sample-based approximations. I think Alex will tell you how long it takes to run some of her models for theory of mind. This is even more so the case when we're modeling agents thinking about other agents thinking about them, where we can have this kind of recursion in theory of mind, which leads to this kind of infinite loop of reasoning. And we might also want to consider potential heuristics that allow people to reason so deeply about other people's hidden mental states. And then just to kind of conclude, ultimately, what we're trying to do is capture both the sophistication of social learning, but we also need to kind of figure out what are the trade-offs, right, of needing to simplify individual learning mechanisms as well. As we're focusing on the social learning side of things, we might need to bracket out some of the complexity of individual learning mechanisms, right, in terms of how we build abstractions, how we learn from experience, how we're maybe differentially influenced by positive or negative outcomes, right? So we can't capture everything simultaneously. And so as we build in complexity in some aspects, well, we're naturally going to have to discard some of the complexity in others, right? So ultimately, our models can't capture everything. We can't build that map the size of the empire, but rather we should try to target our models to focus on the key mechanisms that we're interested in. We have some recommended readings as well. This computational modeling book is an excellent first start. This is kind of where I got my start in cognitive modeling by a summer school run by Steve Lewandowski and Sun Farrell. This book by Richard McKelvey provides one excellent and also very artful and poetic guide to to Bayesian probability theory. You probably never would expect that from a textbook, but it's quite a renaissance piece. This book on Bayesian cognitive modeling is also very excellent. And Berto has this fantastic resource with interactive code notebooks as well on for agent-based models of cultural evolution.